Hello everyone, in this video we are going to talk about dot product. So as the name suggests, dot product is the product of two vectors. First, let's review the previous vector operations that we have covered in the previous videos. If we have two vectors and we're going to add them together, we cannot simply add the magnitude because vectors are also known by their direction. So if we have a vector of 4 and 5, let's say Newton, we're talking about a force here, we cannot simply add them together, say 4 plus 5 is 9. We have to use either a parallelogram rule, triangular rule, or add the Cartesian component of the two vectors. The other operation that we covered was vector and scalar multiplication. So if you have a vector A, and then you're going to multiply it by a scalar, let's say 2, only the magnitude is multiplied by the scalar. So if that's A, that's 2A, without any change in the direction. For vector multiplication, there are two different vector multiplication with two different mathematical operations and also the applications, dot product and cross product. Today we are going to talk about dot product. So the dot product of the two vectors is defined as, let's say we have vector A, I'm going to write it in Cartesian form, AX, the I component, AY, J component, and then AZ. Vector B with three components in three-dimensional. And we have our two vectors and we can perform dot product. So the dot product of the two, A dot B, here in this class, we are not going to refer to multiplication of the two vectors because it's a vague term, whether we are talking about dot or cross product. So A dot B would be the first AX times BX plus AY times BY plus AZ times BZ. So that would be AX, BX plus AY, BY plus AZ, BZ. Also, another definition, A dot B would be the magnitude of A times the magnitude of B cosine of the angle in between. So if we have a vector A, and then we have a vector of B, and we have the angle between the two. For dot product, we could use either of formulations. So one thing that you can notice is that the result of a dot product between two vectors is a scalar. Here I did not use I, J, or K. So the result of two vectors, the dot product of two vectors would be a one value. That would be a scalar value. So I'm going to write it here because it's very important. The result of a dot product is a scalar. It's not a vector. The result of a cross product is a vector, but the result of a dot product is a scalar. Looking at the two definitions of dot product here, AB cosine theta and multiplication of each component, we can come up with one application for dot product. If we set the two right sides equal to each other, we can find cosine theta with the angle between the two vectors. For the first application of a dot product, we call it application 1. We'll be finding the angle between two vectors. We'll be finding the angles between two vectors, or we can even think of it between two lines. Or intersecting lines. If I set the two sides equal to each other, I can find cosine theta. Sine theta would be ax bx plus ay by plus az bv a times b. Here they are both a scalar value, so it's just normal scalar multiplication. So if I have two vectors and I want to find the angle between the two vectors, that's the equation that I use. It can give me the angle between the two vectors. So we are going to solve an example of dot product here. So example, find the dot product of vectors. We have two vectors. You're going to find the dot products. Let's have a numerical example, 3i plus 4j minus 2k. And our vector b would be 5j minus 3k. And we're going to find the angle between them as well. So let's write it here, and the angle between them. And the angle between them. So a dot product, based on definition, A dot B would be the first component 3. Here we don't have any I component, so that would be 0. Plus 4, that's the second component, times 5. Plus the third component of vector A would be negative 2. That would be negative 3. Equal. This one would be 0. This one would be 20. And this one would be 6. That would be negative times negative would be positive, so that would be 26. A common mistake that I see in homeworks or exams that the students use I and J and K here. Again, the result of a dot product is a scalar value. So we found the first part of the problem, 26. And then the second part asks for the angle between the two. We know cosine theta would be A cross B that we found here, A dot B, and then A magnitude of A multiplied by magnitude of B. So here in the numerator, I have 26. In the denominator for A, I need to find the magnitude of A. So that would be 3 squared plus 4 squared plus 2 squared. So that would be 9 plus 16 plus 4. Magnitude of A, magnitude of B would be 5 squared plus 3 squared. So that would be 25 plus 9. And I can find the angle here. The second application of a cross dot product is finding the projection of a vector parallel or perpendicular to a line. So application 2, but not only we are interested in the mathematical operation, we are going to use this operation to find a projection of a vector or the angle between the two vectors. So the application is as important as the operation itself. So finding the projection of a vector parallel or perpendicular to a line. So let's say we have a vector f, we have a force here. I'm going to find the projection. Let's say point B, this is point A, this is point B. I'm going to find f AB, the projection of vector f on line AB. That's the parallel component. Also the projection of vector f on line perpendicular to line AB. So FAB perpendicular would be this line. Parallel and perpendicular. If you have a force F, you're going to use dot product to find it. And if you want to find the parallel component, FAB parallel, that's how I show parallel component, would be F dot UAB. What is U? Is the unit vector. What is the unit vector? Is the position vector divided by its magnitude. I can also write RAB, the position vector from A to B over its magnitude. And you know how to find a magnitude of a vector. It would be a square root of each component squared. So that's another application of a dot product, F dot UAB. And the result would be a scalar. So I can get the magnitude of this vector, the projection of this vector on this line. You might say that, okay, previously we used f cosine theta to find a projection. This is saying the same thing. The other definition of dot product was, if I want to write dot product definition here, f dot UAB means the magnitude of f times the magnitude of UAB times the cosine of the angle between. I know the magnitude of a unit vector is 1, so that's f cosine theta. So it's similar to what we previously know for finding the projection. But here, if you have it in a vector form and you have the dimension, not the angle, you can easily use dot product definition to find the projection of a force or any vector on the line. So dot product of a vector with a unit vector gives us a return the magnitude of the vector along the unit vector. So that's, I'm just writing what we just talked about. So here, when you have a dot product of the force F, UAB, you get a magnitude. If you're interested in a vector form, how can we change a magnitude to a vector? You just need to multiply it by UAB. I use multiply because I'm talking about the multiplication of a scalar with a vector. So if I want to find FAB, the parallel component, but in a vector form, that's what this arrow is representing. I have FAB, the parallel component, times UAB. Not dot product. One of them is, this is a scalar. This is a vector, so it's simple multiplication. Multiplication of a vector by a scalar. I get it in a vector form. But here I get a magnitude. I can show it by the magnitude sign, but it should be obvious the result of a dot product is a magnitude. Also, now that we have the parallel component, if I want to find the perpendicular to the line, the projection of force F perpendicular to line AB, I have FAB. This is the sign I use for perpendicular. I have my vector F minus FAB, the parallel component. Again, this is vector summation. Subtraction is also a subcategory of a summation. So if a vector F has two components, perpendicular component and parallel component, if you subtract the parallel component, you're going to have the vertical component. And if you write these vectors in Cartesian form, that's how we find it, by multiplication of the unit vector, subtraction would be subtraction of the component. So in summary, dot product had two definitions. Either we can multiply the components together, or we multiply the magnitude times the cosine of the angle in between. And it had two applications. One was finding the angle between two vectors, the other finding the parallel and perpendicular projection of a vector on a line.